Hello, everyone. Thank you all for coming on this final session at GOTO. I hope you guys have had a good conference. I've certainly enjoyed it. So today we're going to be talking about two subjects which I find pretty interesting, which is the concepts of services, microservices, which this whole track's about, and then this concept of stream processing, and particularly actually around this idea of a retentive log. So my name is Ben Stopford. You can get me on Twitter there, and I work at this company called Confluent. Anyone heard of Confluent? Got a few. Anyone heard of Apache Kafka? We got a lot more from that. Okay, cool. So this is the company that runs, or it was set up by the original authors of Kafka. So we sort of provide services around it. And I work as an engineer. Well, I actually do a few things. I have a slightly strange role. I do a little bit of this kind of talking stuff, and I work primarily as an engineer on the distributed log part. There's a few different parts of Kafka. And I used to work at ThoughtWorks and a few other companies in the UK. So, yeah, so just thinking about microservices, there's been a really good set of talks so far where we've looked at event-driven approaches and we've looked at request-driven approaches. And we're going to think a little bit about how these things kind of pan out over time, particularly from a kind of architectural perspective. So microservices, they're slightly polarizing in terms of what people think of them. And there's a good reason for this. They can go very wrong. We've had some talks about that too. So for a lot of people, they're about splitting the monolith. So splitting the monolith is important as an idea simply because you're probably going to start with a monolith, right? If you're sensible, you will start with a monolith if you're trying to get something delivered for your business. But you quite often want to extend that. So I think Randy Shoup had quite a nice quote on this, which is, if you don't regret the architectural decisions that you made previously, then you're probably over-engineering. And I think that's very true. But this idea of just splitting a monolith isn't really what microservices are about from my perspective. For me, it's really about this idea of autonomy. So autonomy is a little slightly abstract concept, but what it really means is that each service evolves independently. So that's to say, it is its own master. And having a sense of independence allows us to basically spread an application across many different teams so that they can all move independently. So it's independence, this concept of independence, particularly around code bases, release process, et cetera, which really kind of gives services their value. And it allows them to scale. So when we say scale, I don't really mean from the perspective of petabytes of data or billions of users or whatever. I really mean scaling from the perspective of people terms, like scaling your organization as it grows, because that's actually one of the most challenging parts. I mean, we'll be talking about Kafka and K-streams a bit in this talk, and these are technologies that really can deal with scale in the sort of traditional sense, but actually one of the harder problems is scaling in people terms. I mean, if we think about scaling a monolith, we have many examples from big pin-up companies like Facebook through to many other smaller examples where this is a difficult thing to do. What happens as we grow? But in fact, all companies are, to some extent, collections of applications. If you look at any company over maybe 1,000 people, you'll find there's a whole bunch of different applications that have to connect together in order to progress some kind of business goal. And typically, we'll do this with something like enterprise messaging or FTP file transfers. These applications will kind of talk to one another. But it's often an afterthought. It's often just something that we kind of bolted on the end in an attempt to kind of make this thing work. If we think about microservices or SOA, which are sort of similar, certainly historically, very similar patterns, they're really about this idea of re-architecting for a multi-team architectures where each service can actually have a degree of independence. So Pat Helland wrote a really interesting paper it's entitled Data on the Inside or Data on the Outside. Anyone read it? No? There's a reference to it at the end, and I would really encourage it. It's a great paper. But he talks about thinking about services in terms of the data that they hold inside them, inside the service itself, and the data that they expose. And really, one of the things that we have to think about when we move to a service-based approach is actually the data that we share with other services. It seems kind of obvious, but actually we're not typically that good at dealing with this problem. So this external world, the world that sits outside a service, and particularly the data that exists within it, is something that we really should design for. So this idea of independence, this idea of keeping services independent, comes at a cost. If we think about it from an OO perspective, we've all been taught about the concepts of encapsulation. You probably learned about Parnasse at university or learned object-oriented modeling as you kind of grew up. And we know that if we have an object, it contains state and behavior. So here we have an orders object on the left and a statement object on the right. And we know that we will encapsulate our state and our behavior behind a nice, clean interface. This gives us loose coupling, something which allows us to change. This is a sort of relatively intuitive thing to do. Now, if we do this inside a monolithic application, it's pretty easy to get releases out. So let's say we have a requirement from the business, and it involves changing both sides of an interface. We can put those changes in. We can implement those JIRAs or however we go about implementing our requirements, and we can deploy the whole thing together, and it's pretty easy. If we have the same problem in a distributed world, where different teams run different services, it's a little bit more tricky. Because if we have a change which cross-cuts two services, we have to kind of synchronize the releases of these code changes so that it all works harmoniously together. So this synchronization problem is a little bit painful. So services work best where requirements, change, is isolated to a single bounded context. So let's take an example of that. Imagine something like single sign-on. This is like a really good service example. It has a very simple interface, right? Authorize. And the key point here is that it's really unlikely, no matter what change happens to in terms of our business requirements for a variety of different services, it's very unlikely that any of them are going to affect this single sign-on interface. It exists in a tightly bounded context, a little world unto itself. But business services, the services that we actually build and change on a day-to-day basis, these are a bit different. So to take a kind of example from online retail, if we had a data set of customers, a data set of orders, a data set of the product catalog, these will likely proliferate into many of our different services. These are effectively shared core data sets. So they're just they're much more intertwined. Authorization sits over here in a tightly bounded context. So the point is that the future of business services end up being far more tightly intertwined simply because they have these shared data sets that flow and proliferate through different services. So we need this idea of encapsulation, which we all understand intuitively, so that we can hide our internal state and remain loosely coupled. But we also kind of need this ability to slice and dice these shared data sets. We need to be able to get access to them to write new services, etc. And these two forces kind of compete against one another in the services that we build. And the rub is essentially that data systems, databases, Hadoop clusters, whichever one you want to pick, they have little to do with encapsulation. In fact, quite the opposite. Databases, which are wonderful pieces of technology, and they are wonderful pieces of technology because they can contort the data that they hold into a whole variety of different shapes and sizes. So if we think about a service, we have an interface which hides the data on the inside So there's less data on the outside than there is data on the inside. Whereas databases have this massive amplifying interface that allows you to contort the data that they hold into a whole variety of different shapes and sizes. So this leads to this kind of idea of this data dichotomy. So data systems are really about this idea of exposing data, allowing you to iterate quickly and get your work done. But services are really about the idea of encapsulation. It's the antithesis of that, hiding data from other people, from other services, so that we can protect ourselves against future change. So who's heard this said? Microservices shouldn't share a database. Probably quite a few, I'd imagine. Sam Newman talks about this a lot. Matter of fact, he basically wrote a whole book on it. This is good advice. And it's good advice for that real reason. Databases form one of the richest forms of coupling. They have an amplifying interface, and they also represent shared mutable state. We all know as programmers that we've been trying to get rid of shared mutable state from our programs for many years. So this is good advice. But so what do we do instead for independently deployable applications? Well, one thing we do is we typically wrap our database in a service interface of some description. So we have that data on the outside that's nice and confined, and this data on the inside, and we cleverly create this interface that's nice and clean, and everything looks rosy. So what happens when we release these things into production and we let them evolve a bit over time? So typically you get kind of one of two eventualities. And hopefully these things will resonate with you somewhat. So the first one is that we kind of just end up growing the interface over time. So we might be adding a variety of different parameters onto the end of this interface so that we can kind of get more precise data out of our data service. And this data set on the outside slowly grows over time. Or alternative, maybe we just add more and more methods, right? So we'll start off with get order, and then we have get order by user ID, and then we get orders unfulfilled by ID. And 2 years later, you look at your service interface, and it's got like 50 different methods, all doing really weird, like kooky little things. And you start to wonder if you should have just implemented a declarative language. So this is kind of one way that things kind of go wrong. And actually, as your data sets grow, these problems compound. These data services, which have to service many different other services, have to deal with larger volume. That means they have to be more specific in terms of the way that they slice and dice data. It means that they have more data to vend. They have scaling issues. So that's kind of option one. Option one is we just kind of end up growing this interface over time, being very specific about the data that we vend. Option two is that we just give up and we just move the whole data set. So in this case, we might have a method, get all open orders, where we just poll this service, the order service, pull all of the open orders, and we just keep them locally in a database. We might also do this with a messaging system. And this gives us a couple of advantages. Firstly, it allows us to perform joins, and it allows us to kind of iterate quickly on the data sets that we've got. But it actually leads to a different problem if we go down this approach. And this is actually really the enterprise messaging problem. And that's that we end up with many, many mutable copies in all the different services around our organization. And these things diverge over time. And one of the reasons that this becomes really tricky is that what actually happens is each service, so data in companies is generally pretty crappy. It's just a fact of life, right? Data sets tend to be pretty crappy. One of the main reasons for this is that the way that we interpret data is somewhat subjective, and big organizations have whole departments which will kind of try and disseminate the definition of various different attributes so that you can understand what data means. But what this really means is services end up actually writing software which fixes the problems in the data that they're getting, converting it to their own domain model, cleaning things up. And by doing so, they actually become dependent on the very problems that they're trying to avoid, the very idiosyncrasies in those data sets. And this makes them very hard to change, because if you change something at source, then you've got a variety of different services that are effectively dependent on the previous broken version of the data. So it's very hard to fix these kind of problems in retrospect. So the more mutable copies of data that we have spread around our different services, the more data will likely diverge over time. So what we end up with is this cycle of inadequacy. So we start over here on the left. We've got our new projects. We've done our design. It looks really cool, and we're really happy with it. We've got design on a whiteboard. We do a proof of concept. It's still looking pretty sexy. And we have started to put it into production, and things kind of change. And we kind of work out whether or not we can change our services. Well, initially we can. It all works quite well, so we just keep broadening this contract. And maybe we're probably doing OK at this point, so we'll probably iterate a few times on that. If we've ended up creating a massive shared data God service, somebody might notice that they're spending rather a lot of money, in which case we'll end up going back to this, let's encapsulate and returning back to our nice niche services through some cycle of regeneration. Alternatively, we just go frack it, and we just get all the data. So everyone ends up having a copy, and we end up with this divergence over time. And then the divergence causes a redesign, and we end up going around this circle again. And I've seen this happen a few times in a few different companies. And the thing about change is that when you reinvent something, when you do something for a second time, the thing that's really important is that you actually change the context in a way that implies you're going to succeed the second time. So you might argue that doing the same thing again and again with the same tool set is somewhat idiotic, in that you're constantly trying to bang your head against the same brick wall. So the route out of this is to try and change something. We need to change the way that we actually approach these problems of disseminating data and controlling data across a variety of different services. So these forces are fundamental. Accessibility, divergence, coupling. They affect all of the systems that we build. There's not much we can do about them because they're fundamental. All we can really do is reposition ourselves on the trade-off curve between them. So is there a better way? Is there a way that we could do this, attack this problem in a slightly different way? So this is an approach which I've been working on for a few years with a few different companies, and is actually similar in some ways to a lot of the things we've been talking about today. So the first step is that we build on a backbone of events. So rather than starting with sort of requests and commands and queries, we start with an asynchronous protocol, one that embraces asynchronicity, both in terms from a technical perspective, but also from the perspective of real-world asynchronous problems, like taking an order and getting it to your door. And then we layer in requests where necessary. So request-driven approaches have high coupling, because effectively a single call stack is coupled throughout the dissemination of that call stack. Whereas this event broadcast approach, which is like traditional messaging, provides us with less coupling. We're decoupling ourselves by adding a broker and then using a broadcast protocol. So we want to start with something like this and layer the request-response approach on top. So what we end up with is something, an event-driven architecture, essentially. So we have an asynchronous message flow. In this case, we have an order which goes through a variety of different states. We have a number of different services which are collaborating to progress that thing forwards, all using an asynchronous protocol. And this is termed event collaboration. And then we'll layer queries on where we need to. So in this case, we have a basket service, which responds to a user interface in a request-response mechanism. And we're going to layer that onto our asynchronous architecture. So that's step one. Step two, this is the bit that's a little bit different to a sort of traditional approach, is to make this data on the outside, these shared data sets, a first-class citizen. So this idea of there being data which we expose to other services and data which we internalize. So we're going to focus on designing for this and making these data sets available to any service that needs them. So stateful streams help us with this. So this is effectively a messaging system. I'm obviously talking about Kafka in this instance because it's the one that I know best, but there are others. So we have stateful streams at the center, and we have a variety of different views, which we're going to embed into our various services. And actually, what we're going to do is we're going to use this tool set as a way for manufacturing views based on a central canonical set of streams. So Kafka is the tool that helps with this, certainly from the point of view of this talk. Kafka is a streaming platform, if you're not familiar with it. At the center of it is a distributed log, and then around that there are ways to get data in and out. There's connectors which will allow you to pull data from a whole variety of different data sources or push them into a whole variety of other data sources, or data sinks, and a streaming engine which you can bolt over the top or embed right inside your service. So the distributed log is effectively a messaging system. It's a little bit different to a traditional messaging system because it's designed to scale linearly, from all three layers. So regardless of whether you're talking about the actual log itself, the distributed log itself, or services which are consuming from it, we can take a single pipe and spread it across as many machines as we need to. It's linearly scalable whilst retaining strong ordering guarantees within a single partition. It also provides transactional guarantees in the next release. So that's coming out this summer, in a month. And this is quite interesting because one of the big problems with building distributed asynchronous systems is you really don't have a lot of transactional guarantees, and actually you have to implement idempotence in pretty much in any asynchronous service. So having a scalable mechanism for handling transactions is pretty useful. So what we end up with is this kind of service backbone. It gives us a few different things. We have the ability to naturally load balance. We have fault tolerance, both built into the broker itself as well as built into your services, because data is effectively routed to different instances should an instance of a service fail. We have this idea of transactions, which allows us to implement both idempotence as well as transactionally submitting different messages to different topics and then bringing them back together in a transactional way. But these are the two things that are probably most formative for what I want to talk about today. One is the idea of the log itself. It's a very simple data structure, right? It's basically just like an append-only file. And the nice thing about append-only files is they are O of 1 for read and O of 1 for write. That's very different to a traditional messaging system. So a traditional messaging system is basically built on a B tree. Right? It's a B tree, which means that you kind of have to keep that tree in memory if you're going to have efficient performance. Whereas if you have a log, you can traverse it. It has a very simple interface. It's like seek or scan, but you can implement that in a very efficient way, from whether you're in memory or on disk. And then you have this other feature which allows you to compact a log based on a key. And this is kind of interesting. So a log is literally just an immutable stream of messages, but you can compact it based on a primary key. And when you compact a log, what you get is something that looks like a table. So this is an interesting place for us to keep data on the outside, data that lives between our services, somewhere we can leave it and refer back to it later. So we might have our orders, customers, payments, and stock. We might keep those inside the distributed log. And what we'll actually do is we'll layer views inside our services, either directly inside the service process itself or as a sort of separate service that we refer to inside some bounded context. This kind of starts to change the way that we think about data and the problem of managing shared data in the service architectures that we build. So stream processing is a sort of layer on top of this. And this really helps us do a number of things because it allows us to introspect the streams in a way that's very efficient and lightweight. We're really not taking a deep, long-lived copy of the data. So a little primer on stream processing. Stream processing is really just this problem of working out how to bring together various different continuous streams of data. So it's a machine for combining and processing streams of events. So stateful stream processing is actually a sub-branch of stream processing. And the reason it's called stateful is because it has a bunch of tools which allow you to maintain state. And what that really ends up meaning is that you can treat streams as an infinite thing, which you chop up into windows. Or alternatively, you can treat a stream as a table, something which is deduplicated by a primary key. So we've always got this flow of data coming towards us, whether it's a stream or a table, it doesn't really matter. And what we're actually doing inside the stream processing engine is we're just accumulating some data. And the difference between a windowed stream and a keyed stream, a table, is just how we accumulate that data. So in a windowed sense, we might keep a week's worth of data inside, accumulated inside our service or inside our streaming engine. Or alternatively, we might accumulate that data by key and actually have the entire data set. So for example, if we wanted to have a lookup table of customer information, we just accumulate the customer stream by customer ID, and then we can refer to it within our service, within our engine. So beyond that, obviously, you have the basic primitives of a database. You can take a view, you can join different streams together, streams and tables. You can apply predicates, filters. You can aggregate. You can translate something to your internal domain model. Well, it's really basically just a database embedded inside your service, which allows you to slice and dice these various different streams. So this is basically a way that we can get access to and process data from lots of different services without having to, A, put responsibility on them for providing scalability properties, etc. But it also, most importantly, it allows each service to retain control of the queries that it runs. Right? So the data is shared, but the queries themselves, they're totally owned by each service. So each service has autonomy. So stateful stream processing has this idea of streams and tables on the way in. So here we have an example of a query. This is, again, an online retail example where we're calculating how long it takes a payment to occur, to complete inside a bunch of different regions. So maybe a payment takes, I don't know, a few seconds to process in India and 5 seconds to process in South Africa or somewhere. So it's that kind of query. And we're, in this case, going to do it over a one-day window. And we're actually joining two streams, which are going to be windowed, and we're referring to a single table, all within the stream processing engine. So we have streams on the way in, tables on the way in. And then likewise on the way out, we have a choice. We can either have a stream on the way out, which is the result of that query, constantly updated, or alternatively, we can materialize that as a table we can query. So we can put like a REST interface over it and just query it from a browser. So we have this idea. So I guess, yeah, so the important point about this is that we're overflowing data to RocksDB. So that's the internal implementation inside the streaming engine. So that's really just an optimization so that we don't have to keep all of this data in memory. And we can obviously spread this over many instances of a service. So to take a little example, imagine we want to trigger an email every time a payment is confirmed. So we send the user an email that says, your payment's confirmed for this particular order that you just made. We might want to do a join between payments, which we'd probably treat as stream, orders, which we would also treat as a stream because those two things are likely to come at the same time or within a defined window. And then we might just use a lookup against the stock table. And the stock table is, so this whole thing would be done inside this one service. And we're joining, as I said, two streams and a table, and then sending an email. So we might not want to do this with a streaming engine. Streaming engines have an API which you have to learn, or we might have a database. We might have a requirement for doing ad hoc queries, something that where we want something like maybe Elasticsearch, or maybe we want a relational model, whatever it might be. So we can always just go back or evolve to using a standalone database. We just use a connector and do the join there. It's just a slightly heavier weight process because we're going to have to then curate that data over time. But the interesting thing about this is that if we take even just this approach with the database, if we did this in a traditional messaging way, we basically have to keep all of the data. We have to keep all of the data over time so that we can work out, or so we can answer the questions that we might need to answer in order, in this case, to solve this problem and actually any future problem. Whereas the nice thing about having the shared streams is that the connector can basically just take the view that we need right now. We literally just take the bits, the very specific query, the very specific materialized view that we need to solve our problem today. Because we can always regenerate it. We can always go back and regenerate it again. And actually, a lot of the mechanics of getting this pattern right, and I'm not going to go into this today because it's a much bigger talk, but a lot of the mechanics of getting this particular right are about having an iterative process for rebuilding these data sets. That's really about having the machinery. It's more like a kind of continuous deployment approach. So we have this idea of shared storage inside a log, and we have this query engine which we can embed inside our services. So data storage plus query engine is a kind of database, right? We've got data inside Kafka, query engine sitting on top. It's kind of a database. But we actually have many services, right? So we have one central set of canonical streams, and then we have a whole bunch of different services. They're all using the same retentive set of streams, but they're all implementing their own views, their own interpretation of that shared data set. So this is like a shared database. It's basically a database inside out. Has anyone seen Martin Kleppmann's talk on turning a database inside out? We've got a few. Yeah, that's a really good talk. I would encourage you to see that also. It's a kind of quite a powerful idea. So we sort of started with this idea, right? Microservices shouldn't share a database. This is kind of a shared database. But it's not a normal database. We can actually prove, not by me, by the way, people have done a fair bit of research to prove that event broadcast is the lowest form of coupling. And the reason for this, intuitively, the reason event broadcast is the lowest form of coupling is because each service only really receives a stream of events, and it can basically do whatever it wants. But if we centralize something that's immutable, we don't actually affect coupling. So this isn't any kind of shared database. We certainly can't make a coupling argument for why this would be a problematic approach. So to share a database, we should think about turning it inside out. And what we end up with is basically a machine which allows us to create these kind of materialized views. So we have the orders, the payments, the customers, and the stock. These are the canonical data sets. And we have a variety of services which simply have a process for manufacturing the views that they need to do their job in a very lightweight manner. You can always go back to the shared streams if they need it. So let's look at these different. So we've got basically 4 different approaches to sharing data. We have shared database, service interfaces, event broadcast, stream data platform. And then up here we have ease of change, like how easy is it for us to evolve our system, data accessibility, how easy is it to get something up and running quickly, and then data erosion, that issue of things diverging over time because they're effectively mutable. So shared database is pretty bad from ease of change. It's like shared mutable state, not good. Great from a data accessibility point of view, because anyone can just dip into it. Great from a data erosion point of view, because there's just one canonical copy. Service interfaces are a little bit better from the perspective of ease of change, but not much, right? Because we still have to, if we've got a new requirement, we still have to get our service interfaces to change in order to give us the answer to the new question that we have. From a data accessibility point of view, it's okay. And from a data erosion perspective, it's good. One canonical copy. Event broadcast, great from the point of view of ease of change because everyone's basically got everything. They can do whatever they want. Not so great from the perspective of accessibility because if you weren't listening to the message when it was sent, then you don't have it anymore. And from a data erosion perspective, it's poor because you have to maintain these copies of shared data sets over time. But if we do use this kind of log-backed stream data platform approach, it's easy to make changes, it's easy to get access to data, and we don't have this issue of data erosion in the same way because we're actually building these very focused views which are backed by this shared data set. So, for me, good architecture actually has very little to do with drawing something on a whiteboard or coming up with a design. Good architecture is really about providing a technology stack which you can evolve over time. That's actually the hard bit. The hard bit is going, how do I start from something small and evolving to something that's complicated? That's hard. For me, request-driven approaches aren't enough. And I think that's fairly well understood today. High coupling is hard to handle physically asynchronous flows, things that happen asynchronously in the real world, and it's hard to move and join data sets. So we want to embrace this data that flows between services, this data that sits on the outside, and actually make it something we design for, so that we can give our services independence. Right, so each service has the freedom to change and manage its own data based on a canonical set. So we're building on a single stream data platform that everyone can access and share. So this is a mechanism for evolving an architecture efficiently over time. And there are kind of a set of principles that sort of back this idea up. It's wimpy, where we start simple, lightweight, and fault tolerant. Immutable, because we want to build on a retentive shared narrative. Reactive, because we want to leverage asynchronicity. We want to focus on events which are coming now. Evolutionary, and that's actually pretty important. It's this idea that we only take the data that we need today. That keeps us lightweight and nimble, and decentralized. So we're receiver-driven. Didn't really talk about that today, but that's what gives event-driven architectures their decoupling properties. We're avoiding coordination and we're avoiding God services. And that's all I had to say. There's a number of references here. We've been working on a series of blog articles on this, and there's the Turning the Database Inside Out talk, which is excellent. There's 2 papers there from Pat Helland, which are really good. and a couple of things from Jay and Neha, who work at Confluent. Thank you very much for staying for this talk. I hope this has been useful. If you have any questions, then maybe you've got some through the app. You can ask them now. I'll be around for the drinks and stuff. So I love talking about this, so please come and talk to me, give me your thoughts, argue, whatever you like. I love to talk about it, so please do. And I said, or you can get me on Twitter. Thanks very much.